Okay, good afternoon. Let us start our lecture. So today we start talking about statistics. So we start with population samples, and then we talk about statistics and the sampling distribution of statistics. And later on, we'll also talk about law of large numbers as well as the central limit theorem. So the idea is that, okay, I have a collection of objects or subjects, and we are interested in some of the characteristics of this population or this collection of objects. So for example, we talk about a population of those who take ST2334 for this semester. So we would like to know what is the average what is the average CAP for this population. So one way to do it is to get everyone's CAP and then take the average. So that is the average of the population, the average CAP of the population. So it's not a group, about 500, so maybe still manage to get the CAP everyone. But what happens if the population is so huge that we may have problems in getting to know the characteristic of each of the individuals in the population? So what we're trying to do is to look at a subset of the population. All right? We call this a sample. And then study this sample. So for example, I want to know the average of the CAP for this group of students taking ST2334. Then what I do is take a sample. Let's say take 30 students from this group and look at their CAP. Then how to link up this group of students CAP with the population mean. So that is statistics. So naturally, we'll think of taking the average of this 30, average of the CAP of these 30 students. So we got a number. So that one is a value that we are going to estimate or guess the population, the average, the population average CAP. All right. So then you may ask, so can I take another sample? If I take another sample of 30 students, then will the CAP, average of the CAP the same? And of course, it's unlikely that they are the same. So if I take a third sample, then I have another average of these 30 CAPs from the third sample, and so on. So I can take many samples. And at the end, I have a lot or many sample values. So now, which one should I use to estimate the population average CAP? So before we answer that question, we should ask ourselves, how does this sample average, each sample gives an average, so how does it behave? So that is called sampling distribution of a quantity. In this case, it's the average, the sample mean. So what is the sampling distribution of the sample mean? All right. So so that's what we are trying to discuss throughout this chapter. All right. So first of all, population and sample. So a totality of all possible outcomes or observations of a survey or of experiments is considered as a population. A sample is just a subset of the population. All right. So every outcome or observation can be recorded as a numeric or categorical value, and thus each member of the population is a value of a random variable. All right. So because each one, the outcome or the characteristic, all right, can be varied. Okay, what I mean is that because of course, for example, the height or the CAP, that's now I mentioned, CAP of individual. So everyone has their CAP. But before I check, I don't know what your CAP. So your CAP can be ranged. No one will be 0, right? So maybe 1.5 up to maybe 5. You strict A, so you got 5. All right. So yes, you have a particular value, but to us, I don't know your value. So to me, it's a random variable. You rate your CAP range from maybe from 0 to 5. Okay, let's say, or 1 to 5 is more reasonable. 1 to 5, any values between 1 and 5. So after I check or ask your CAP, then I got the realization. I know that your value. Just like when we talk about toss a coin, it's head or tail. You don't know whether it's a head or tail until you toss the coin and get the outcome. Then it is a head. Then that's the outcome. Or it's a tail, then it's the outcome. So the same applied here. So any characteristic before you measure or you know that is considered as a random variable. It takes certain values with certain probabilities. So, for example, CAP equals 5. So, I believe it's less likely to have a CAP equal 5. If I just ask a student, I pick a student from this group, and then check his CAP, I will believe that these students have a CAP equal to 5 will be less likely than a CAP with 4. Why? Right? Why? You don't believe me? I'm so smart. Mine is 5. All right? I'm talking about the population. All right? So if everyone is 5, then we have no more random variable. That's because we have some 5, some 4.9, 4.8. And then, in order to get 5, you mean every module you have to score A or A+. Not all the modules, not all will get A or A+, right? Some will got A-, B+, and so on. So in other words, it's likely that your score will be close to the center of the distribution. And 5 is definitely not the center. All right? Anyway, this is what we mean by each member of a population is a value of a random variable. All right? Okay, so there are two kinds of populations, infinite and finite. All right. Okay, so first of all, let's look at the finite population. So that means the population has a finite subjects or finite records or finite number of elements. All right. I have to stress that when I say there's a finite elements in the population, it does not mean that, all right, okay, suppose I say that this population has 1 million of elements. It does not necessarily imply that all these 1 million elements are of different values. It can be just 0 and 1s. I have 1 million values, either 1 or 0. All right? So you have to distinguish the number of elements, that means how big the population is, and what are the distinct values of the variable. All right? So these are two different things. One is the size of the population, or the size of a sample. All right? The other one is the distinct values. All right? So each element will have a values, but there may be repeat. All right, so just like I said, 0 and 1, only 2 values, success and failure. Out of 1 million units or 1 million elements, so there are only 0 and 1. So there are only 2 values there. Okay, so for instance, all the citizens in Singapore, all the books in the science library, all the students taking the ST2334 for this semester, so they're finite. All right. Now, population is in statistics, the population does not necessarily mean that it's the ordinary sense of population. Singapore, what's the population of Singapore? Do you know what's the population size of Singapore? Roughly 1 million, 2 million, 8 million, 5 million, 6 million. Okay, you check, all right? It's not 1 million, it's not. 5 million, okay, close. All right. What I mean is that, okay, this is the normal understanding of the word population. But in statistics, population is just a collection of something. And then this something, each one will have a characteristic or will have a value. Maybe more than one value. All right. Like your CAP is one characteristic that we're interested. Or maybe your height or your weight. All right. Or how much your household income is, or how much you got, right? From your tuition, from your scholarship, or whatever. So all these are characteristics of an individual. All right. So how about infinite population? Now this one you have to be careful. Infinite population, there are two types of infinity. All right. One is countable, but you still don't know how big it is, but you can count. 1, 2, 3, 4, 5. That is called countable infinity. That means this population, everyone you can give a number. But this number these numbers do not have a largest. Cannot stop. You can keep going. Uncountably infinite is even worse, or not even worse, even bigger. Okay? So it can be you cannot count. So how big is this number? Wow. Just ask yourself, between 0 and 1, how many pawns are there? Right? No matter what you get, any 2 pawns, we can always have another pawns in between. All right? So that is uncountably infinite. All right? So you have to be aware of these two. So, to make things worse, we also have this considered as infinite population. The results of all possible rolls of a pair of die. You roll a pair of die. How many possible outcomes are there? 6 outcomes for one die, another 6. So altogether, there will be 36 outcomes. But you can roll many, many times. All right? So the outcome will be an infinite population. But there are only 36 distinct values for each of the outcome. If 1, 2, it represents the first die is a 1 and the second die is a 2. All right? Random digit numbers taken with replacement from a sample space of 10 digits. Now this word is with replacement. This is a very crucial information to distinguish or to tell you how about what is the population. So the population in this case is infinite because you can repeat again and again. All right. So it's considered as an infinite population. Although there are only 10 distinct digits, but you can repeat. Okay, you select, let's say the first one is a 1, all right, that's the first outcome. Then you put it back, so the 1 can be selected again. So you still have 10 digits, you can select 1 out of these 10. So you can do this, keep doing this. So it's infinite population. So just remember, with anything that you do with replacement, then it's considered as an infinite population. The depth of all conceivable position of a lake. All right? So in a lake, you consider depth. All right? So there's infinite number of ponds that you can measure the depth. So it's an infinite population. All right? So some finite populations are so large that in theory, we assume them to be infinite. All right? So, such as the population of the lives of a certain type of storage battery being manufactured from a factory. So the factory can produce many, many batteries. All right? So in that case, it's considered as an infinite population. Although it's not really infinite, but the number of batteries that a factory produces may be very, very, very large. So we consider it as an infinite population. Okay. So just now I mentioned that if you want to know something about the population, we look at a subset of it. All right? So we call that subset a sample. But the statistical theory that we are going to discuss are based on random sample. This word random, all right, to describe the sample is to make sure that all the theory are work. All right? So this random sample has a definition. Okay, okay. There are many types of random sample, but we just talk about this simple random sample. So the idea is very simple. In this population, all right, we try to select a subset of size n, right? Then a simple random sample of n members. That means this sample has n elements or n individuals. All right. Is in such a way that every subset of n observations of the population has the same probability of being selected. All right. So that is a simple random sample. So suppose I have a population 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Only 12 individuals. I want to select a sample of 3, a subset of 3. All right? So I randomly select. That means any 3 of them have equal chance of being selected. How many sample of 3 that we can select out of 12? So it's 12 over 3. So this is the number of ways that you can select 3 out of 12. So that is how many samples that you can get. So one example of sample is like this: 1, 8, 9. 1, 8, and 9. So this is one sample. Altogether, there are so many samples out there. All right. So each one are equally likely being selected. All right. Okay. So can I just have everyone have equal chance of being selected? All right. So let's say I have 12, right? So if I select randomly so each observation are equally likely being selected. So let's say 112. All right. Now, if I decide that I'm going to select the sample in the following way. Once I got, okay, I want to select 3, right? So once I get a number, let's say 4, then I will take all the elements, all right, according to this range. So the next third one, all right, first, second I skip, and then third one. So once I select 4, I take 7, and then I take 10, and also go backward. I take 1. So sorry, I want a sample of size 3. So sorry, let me repeat it again. So if I have 4, I will take every 4th. So I will take 4 and then 8. And the next one, skip the first one, second one, third one, and take the 4th one. So 12. So this is my sample of size 3. Then if I select a starting point, let's say 7, then I will take 7, skip 8, skip 9, skip 10, so I take 11. But I also have to go backward, all right? Because after 11, I cannot, okay, you can consider that you continue. 1, 2, 3, and so on. So the next one is 7, so it's 3. All right. So this is the sample. Now, we also, by doing so, this is called systematic sampling. We have a probability of 1 over 12 for each unit being selected. So this is not a simple random sample, but it has the property that each one has the same chance of being selected. But 1 cannot go with 2. 1 will go with 5. All right, so 1, 5, and 9 will be one possible sample. 1 cannot go with 2, cannot go with 3, the way that I select. So this is not considered a simple random sample. But anyway, you just have to understand that for simple random sample in statistics point of view means that this particular sample, all right, any combination, any selection of this little n from the big sample, from the big population are equally likely. So that's the main point. All right, so for example, I have 20 mice and we want to select 5. All right, so one way to do it, remember I mentioned it before. So I have 20 mice, some big, some small. So if you look at the 20 mice and then try to select 5, you may select 1. Oh, this is quite big. I try to balance it, I choose a small one. So it's not random from statistical point of view. All right. So what we do is to give label the easiest 1 to 20. Each mouse with a number. Okay. Then forget about the mice. Look at this 20 number. I randomly select 5 out of these 20 numbers. All right. So this is from Excel. So if you don't get it, it's fine. It just in practice, if you want to select randomly a number of units or elements or subjects from a population, then you can use this one. So the first command is just generate random numbers, no argument. You see inside and nothing inside. Then the second one is the rank. So it's basically saying that you rank this particular cell among this range. This must be among this range. And then this is either 0 or 1. 0 for descending order. You arrange the values in this range in descending order. If the third argument is 0. 0 in descending order, correct. And then 1 in ascending order. Then one more index. So specify the range and then the row number. All right. Okay, how to use it? So here is that. Okay, I enter 1 to 20 a number 1 to 20. All right. In the cells A1 to A20. All right. So I generate 20 random numbers. So put all these 20 random numbers in this B1 up to B20. Then copy and paste the value to another range. Unfortunately, Excel has this very efficient way. Whenever you press a return, they will redo everything. So here, column B, I generate random number. So if I do something else in other cell, then they will change this set of random numbers. So I want to copy, make sure that this is the set of random number I use. So that's why I copy to the third column, C1 to C20. All right, copy the values, copy the values. You see, I have to stress that. Because if you don't specify copy the values, I don't know whether you have experience using Excel. Then they will copy everything. So next time when you press, they will also change for the third column. Okay, after that, I use this function called index. This is the 20 numbers or the 20 individual or 20 population that I want to select from. Then I rank this random. These are the set of random numbers. All right. Sorry. This is set of the random numbers. This is the first random number. All right. So I pick the rank of the first number in this range, All right. Rank according to ascending order. And then this command is copy or you apply to these 5 cells. So that each entry D1, D2, D3, D4, D5, I will get this command. All right. Now let me show you. This is the next page. All right. Let me show you. Okay. Now, instead of using 20 numbers, I give them names. All right. These are the 20 individual. I'm going to select 5 of them. 5 of them. So how to do it? So first of all, I generate random numbers. RAND bracket. So this will be a random number. I copy and paste to the rest. So I generate 20 random number. Suppose associate with each of this individual. All right. But let me show you equal. All right. I can look at the B. So it changed. Once I press return, they will update. That means they will recompute. So this is to generate random numbers. So they will. All right. So I have to copy and paste all this number, only the value. So this is what I've done last time. So these are the 20 random numbers I generated in the past. So I just copy this value. I'm going to work on this set of random numbers. So here, I try to rank this number according to descending order. So that means 1 means that's the largest, 2 means the second largest, and this number among all the C1 to C20 cells, this is the 19th largest. That means it's the second smallest value. All right. Okay. So these are the ranks of the random number that I associate to the first subject, Alex. The second subject, the random number I associate with it is 0.462 and associate with Bill. And this number is among the 11 largest in the set of random numbers that I generate. So this is the 9th. As you can see, where's my 1? 1 is here. 0.989 is the largest random number among these 20 random numbers in column C. All right. Okay. So now then index A1 to A20, this is the population. A1 to A20, these are the population, 20 of them. And I pick up the rank of C1, the rank of this one. All right. So according to this one, what I pick is the 19th. The 19th. So where's the 19th? 19th is Sam. So they pick up Sam. The second number, all right, is 11. Rank 11. So I pick the 11th, which is this one, Kenneth. All right, so that's how we select the 5 numbers. If you don't get it, you try to apply to it. It will not be test, it will not be exam. But this is a way to select randomly a subset from a large set, which I call it population. In this example, I have 20 subjects. This is my population, and I want to select 5 out of this 20. So what I do in the following step. First of all, I generate 20 random numbers. All right. So I just make sure that it won't change because Excel will update. So now I just copy the value to the C column. Then next, I find out the rank according to certain order, ascending order or descending order. All right. So then the next thing is to use this index to associate. So if the 19 is the rank, then I select the 19, the subject with the number 19. So that's how I got. All right, have fun. You can try it yourself. Population, and then try to select, let's say, 10 of them, for example. All right. Okay, so how about sampling from a finite population? So just now we talked about how to select a random sample. So now we try to select a sample from a finite population. This population is even smaller, only four individuals. I call it A, B, C, D. I want to select a subset or a sample of size 2. Size 2. So there are altogether only 6 possible samples. Okay? 6 possible samples of size 2. So there are A, B, A, C, A, D, B, C, B, D, and C, D. The order is not important, all right? The order is not important. So long as what we see is A and B, so that's considered a sample of size 2 with A and B. All right, so, okay, so these are the possible. So, in general, if you are sampling without replacement, which means that without replacement simply means that you select one, you won't put it back, you won't replace it back, and then you select the next one, the third one, the fourth one, and so on. So in this case, the number of sample size, number of possible sample of size n will be choose. This is the population and this is the sample size. This is the population size. Remember, we're talking about finite population, so the size is capital N. It can be 20, just now I showed you 20. It can be 100, can be 1 million. This is our sample size. So this is the number of ways, this is the number of samples, possible sample of size N that you can select from a finite population of size equal to capital N without replacement. So because they're equally likely, so each one should have 1 over choose little n out of capital N choices. All right. So for example, just now we have n equal to 20. We want to select 5. So there are altogether so many possible samples. The one that you just see is one of them. And the probability of choosing that particular sample is 1 over 20 choose 5. So that's what it means here. But even from a finite population, I can sampling with replacement. So in that case, A, B, C, D, we still consider this simple population. I can select A, then after that I put it back. So the second outcome can be A again. So in other words, I can think of it like this. All right. There are 4 ways to choose for the first one. All right. And then the second one still have 4 ways. So altogether it's 4 squared. All right. So if you notice that, basically we have a population of size n, and I want to select a sample of size n. So you can think of it like this. So I have sample size n, so altogether I have little n boxes, and each one I can have capital N. So each one I can select 1 out of the population and put it here. Another one I can also select 1 out of the n individuals in the population. So altogether there will be n times n times n times n. So altogether, there's so many possible samples. If you select the samples with replacement. So in this example, we have AA, AB, all right, and so on. So you can see that you have AB and BA, all right. So it makes a difference in terms of the ordering. So you can have A, B, and BA. A, B means that A being chosen first, all right, in the sample, B as the second elements in the sample. All right. Okay, so these are the possible samples, altogether 16 of them. So in general, okay, we have n to power n samples. And each will have a probability of being selected equal to 1 over that number. If you have 10,000 samples, possible samples, then if they're equally likely, then each one should have 1 over 10,000. So 1 over capital N raised to power little n is the probability of being selected. Okay, then how about infinite population? Now for infinite population, it makes no difference whether it's with replacement or without replacement. The reason is very simple. You have infinite population. So you take one out, all right? No matter what the value are, it won't affect the remaining. The remaining population still looks as if you have the one before you take the first observation. All right. Just like you toss a coin, a head or tail. So you toss it, you know that okay, it's a head. But then will that affect the outcome of others? You still consider as the next outcome is a set of all possible, infinite number of possible outcomes. So it makes no difference whether it's with replacement or without replacement. Oh, sorry. Maybe you should think of it as I have a box. All right. If I have finite number of balls, for example, two colors only, blue and red. All right. So if you take out a ball, you don't put it back, then the number of red ball and blue ball will be different from before you select your ball. Take out a ball, right? Because it depends on what the ball that you take out. But if I tell you I have a magic box, there are infinite number of balls inside, and the proportion of red and blue balls is fixed. So even if you take out a blue ball, it won't affect the proportion of the red balls to the blue balls in the box because there are infinite number of balls. All right? Infinite is very hard, huh? I don't know whether I can see infinite. We cannot see infinite. All right? Ocean is big, but it's still finite. All right? Universe, okay, I cannot say that. I don't know much about universe. Maybe it's still finite, but it's expandable, so it looks like it's infinite. All right? Okay, so for infinite population, it's impossible to proceed as what we just discussed. So we don't have this 1 over n choose n or 1 over n to power n as the probability of each possible sample. So the concept of random sample in an infinite population is a little bit hard to explain. All right? So we try to use the examples to illustrate it. So suppose we consider the results of 15 tosses of a coin. All right? So in this case, we have an infinite population. This infinite population consists of all the tosses of this coin. And we just take a subset, 15 of them. All right? So in this case, this 15 tosses of this coin is considered as a sample. So if the probability of getting a hash is the same for each toss, then, and also these 15 tosses are independent, then we say that the sample is a random sample. All right? So in other words, what I'm trying to say is that, so we have this random sample. In this case, 15 of them. So I can consider I have 15 random variables. So the first random variable, I call it x1, represent the outcome of the first toast out of these 15 toasts. All right? So in this example, because the toasts have only two outcomes, head or tail. So in other words, I'm looking at the outcome is either head or tail. And the probability of getting a head remains the same from the first toast to the second toast. You're toasting the same corn. So the probability of a success of getting a head should be the same for the first toast, the second toast, the third toast, and up to 15 toasts. So what we are saying here is that what you see as a random sample can be considered as a random sample if the distribution or the behavior of each of these random variable x1, x2 up to x15 are the same. In this case, because we have two outcomes, so we can model it by a Bernoulli distribution. That means it's probability of x equal to 0 is equal to 1 minus p, probability of x equal to 1, it is equal to p. So that is how we model a particular xi. But then how about this p? So we're saying that you need this p to be the same, which means that we make sure that every xi's are the same distribution. So we are saying that x1, about this example, this is the random variable, represent the first toast. It's head or tail. So we ask, what is the distribution of this one? Because, okay, so this one is more concrete. So the distribution basically is a Bernoulli distribution with two outcomes, and the probability is represented by p to power x and 1 minus p to power 1 minus x. X can only be 0 or 1. All right. 0 is a failure. All right. Or we're talking about x is the number of success. So success can either be 0 or 1. All right. So now, what is considered as random sample if x2 has the same distribution as others. So all these x have the same distribution. This is only one of the criteria. The second one is that they are all independent. That means the outcome of x1 is independent of the outcome of x2, independent of x3, x4, up to x15. All right, so that is how we define a random sample for infinite population. Because it's infinite population, so the one that we just discussed will not work. Whether it's because finite sample population, you can have this capital N, and you can think of it how many ways to choose and get the definition. Random sample means that every subset of the same size or every sample of the same size should have equal probability of being selected. But for infinite, we cannot define like that. So what we define is that, okay, a random sample is represented by a bunch of random variables, x1, x2, up to xn. And each of them has the same distribution. Same distribution. Not only that, all these xi are independent. Because of that, of these two, oh, sorry. Okay. So, okay, later on we will mention that, in fact, when we say a random sample, it simply means that the John distribution I don't know whether you remember. This one we never discussed it before. We only discussed about two random variable case. So it's equal to this. So it simply means that the John distribution is equal to the product of the marginals of each individual elements in a random sample. So if it's a random sample, it satisfies this. All right, if it satisfies this, then we can consider x1, xn as a random sample from an infinite population from an infinite population. And how to describe this infinite population is described by f of x, the probability, density function or probability function, which is the same as all this. All right. So we'll come back to this. Let's look at another example. All right. So okay. This is what I just mentioned. So each row, all the elements of the population have the same probability of being selected, and success draw are independent. So they have the same distribution, and as well as they are independent. So here is another example. So let's consider, this time we consider sum of all possible rows of a pair of die. So what we are saying is that, okay, I have two dice, I roll them. So I suppose I have 36 outcomes. All right, 1, 1, 1, 2, and so on. But we are not interested in individual outcomes. We're interested in the sum. So we add the two outcomes. So if 1, 1, then it becomes sum is 2. If one die is 3, the other die is 4, then it's 7. 3 plus 4 is 7, and so on. So these are the possible sum values. That means if you roll two dice, all right, the outcome can be 2. That means the sum is equal to 2. Means that you got 1, 1. So you have a 2. Or you roll the die, you got the sum equal to 7. So it can be 3, 4, can be 2, 5, can be 1, 6, can be 6, 1, can be 5, 2, can be 4, 3. So altogether, there's 6 possible outcomes out of 36 possible outcomes. That will give you sum equal to 7. All right. Okay. So this is how, all right, the random, okay, what does this mean? It means that, okay, if I roll two dice, then the outcome will belong to one of these 11 values. It can be 2, can be 3, can be 4, can be 12. How do we get 12? If I roll the 2, I got 2, 6. Both dice are 6. Then I got the outcome equal to 12. So these are the possible values for the outcome. Next, what are the probabilities associated to this value? So we can work it out. So to get and sum equal to 7, it means corresponding to 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. 6 possible outcomes out of 36 of them will give you a sum equal to 7. So that will describe how this one experiment tossed the two dice. Okay, so the values are ranged 2 to 12, and the corresponding probability are given there. So this is the behavior of one outcome. All right. Now, so you can think of it, we have a population which is infinite. You roll the die one time, second time, third time, you can roll it many, many, many times. All right. So now suppose I roll it 100 times. So it's like, or we consider as if we take a sample of size 100 out of an infinite population. Out of infinite rows of these two dice, I just take 100 of them. All right, take 100 of them. So each one supposed to be independent. The outcome of one row of these two die, what do you get, will be independent of what you get in the next row. So I represent the ith row outcome as xi. So I have x1 up to x100. Each xi is a random variable. It represents the outcome of the sum, represent the sum of the row. So xi can be 2, can be 3, up to 12. And they have a corresponding probability which given in the last slide. All right? Then, because all these are random variables and they have the same distribution. All right, the same distribution means that it doesn't matter it's the first row or it's the 100th row. All right, so they are coming from the same distribution. It will not be different from what we shown here, the 2 slides before. All right, no matter it's the first row or the 100th row, the distribution, the outcome will follow this distribution, the sum of the two numbers. All right, so, and since they're independent and they have the same distribution, therefore the probability of the first outcome equal to x1. Okay, make sure that you understand the notation. The capital letter means a random variable. Random variable means that it's a variable, takes a bunch of values and associate to these values a probability or probability density. While the lowercase x1 is the value, the actual value. So in this example, x1, the little x1, means 2, 3, 4, 5, up to 12. So it means that the random variable, when you really roll it, before you roll it, it's a random variable. But after you roll it, you look at the outcome. Okay, the outcome is 3 and 6. So the sum is 9. So now I say x1 equal to 9. All right? So the lowercase is a number, a constant. All right, represent a value. While the capital represent a random variable. Okay, so the random variable x1 equal to little x1, x2 equal to little x2, and so on, is equal to this product. We can do that because all these xi's are independent. So the marginal is equal to the product, the joint distribution is equal to the product of individual probability, but each one has the same probability. So I just write it like that. All right. Okay, so that is how we represent a random sample. All right, so if x is a random variable from a certain distribution, all right, then if x1 up to xn are independent random variable, each have the same distribution of x, then we say that x1 up to xn is a random sample of size n from this population. So remember the first line, simply saying that you can consider you have an infinite population. And how to describe this infinite population? Described by this f of x, the probability function or probability distribution. So a simple example I just mentioned at the beginning, I have a population, 1 million is not infinite, but you have an infinite, like toss a coin, head or tail. It can be infinite number of toes that you can have. Then each outcome is head or tail. All right? So describe this infinite population, it's very simple. I just saying that, okay, because this population have only 2 values, toes the coin, so it is f of x equal to p x 1 minus p 1 minus x, where x equal to 0 and 1, and 0 otherwise. So this would describe the population. This population is the toes, the outcome of the toes, and you can have infinite number of toes of this coin. Then I just toss it let's say 10 times. Then I will have x1 up to x10 to represent it. I have not tossed it yet. I just say that I'm going to toss it 10 times. So the outcome will be represented by this set of random variables, x1 up to x10. So now I toss 1 time, or it's a head. So it's a success. If you consider head as a success, then x1 equal to 1. Then I toss it the second time. It's a head again. So I have x2 equal to 1, and so on. All right? So this, if I have not tossed it yet, so this x1 up to x10, this set of random variables represent a random sample from this infinite population. So that's how we understand the random sample in infinite population. Just remember, infinite population, you have to describe it. How to describe it? You use this f of x, the probability distribution. All right. That means it's a probability function if it's discrete case, a probability density function if it is a continuous random variable. And then each of these x1 up to xn are random variable, and each are having the same distribution as f, the population distribution. And they are all independent. This is very important. Huh? The elements in the random sample are all independent. Okay, so that's what we have, and I mentioned earlier. Okay, so now we talk about a sample x1 up to xn, but we try to talk about a particular function of these random variables, x1 up to xn. So why we want to do that? So here's give you some idea. This whole session is on sampling mean, and on sample mean, how sample mean behaves. So that's about this session. All right. So we start with population. All right, population and unknown population parameters. So for example, I just say toss a coin. So the distribution, you have infinite number of tosses, so it's equal to px 1 minus p 1 minus x, x equals 0 or 1. X represents the number of success. All right. So if x equal to 1, that means you have one success. It's a successor, that means then it is equal to p. The probability is equal to p. But we don't know p. We don't know p. All right. So we try to get some idea what the p is. All right. So suppose we can toss the coin. I got a head. Toss a second time. Toss a third time. If I toss it 100 times, out of this 100 times, all right, if I got 60 heads, consider head as a success. So if I got 60 heads out of 100, then what will you believe the p should be? Or how will you guess the p? So naturally, I just take the average. So 60 over 100. So that is my estimate of p. So that's the idea of what we are going to draw inference from a subset of the population. And this subset is obtained by simple random sampling methods. All right. Okay, so we reach, for example, in this example, we wish to know the proportion of people in Singapore who prefer a certain brand of coffee. So there's a proportion of people or Singaporeans favor a particular brand. So unless you ask everyone, otherwise you won't get the proportion. And you cannot ask, even multinational company cannot ask everyone, and everyone will give the answer. So what we do is to take a random sample. Random sample, random sample. I will not ask just this group of you whether you like certain brand of coffee, because it's not a random sample. All right. So I make sure that I have this whole list of Singaporean, and then I select a subset from this list. All right. Okay. A large random sample is then selected from the population, and then we look at the proportion in this sample favoring this brand of coffee. Then we use this proportion that we get from this sample, try to infer to the proportion in the population. Remember, this is not the answer. This is how we get and guess. Or in statistics, we got an estimate. We guess based on this sample. If another guy get another sample, then he may got another answer. All right. So all these answers, correct or not? We don't have correct or incorrect. All are answers, provided that you are selecting a random sample. If it's a biased sample, then it's not. All right. So that's how we work on this. All right. Now, so we introduce this term, statistic. Statistic, no S. Statistics. In statistic theory, this statistic, the word statistic, is not drawing histogram, look at the mean, all this. Okay, statistics is a function of the random sample, or the x1 up to xn. All right. So a statistics is a function of the this, a function of the random sample, x1 up to xn. So this is a function of x1 up to xn. Is this a function of x1 up to xn? Is this a function of x1 up to xn? Okay, what is a function? Function, that means for any x1 up to xn, any values here, we try to map to some real number, let's say, real number, or something, all right? So here, whenever I have x1 up to xn, I take the sum of them and divide by n. So this is a function. This one, yes, it's still a function. But in this function, I do not care about what is the x1, what is the xn. They are not included in this function. So is this a function? Yes, it's also a function. No matter what your x1 up to xn, always map to 3. So it's a function. But it's useless to us. All right? So it's a function. All right? So how about this? Median. You know what is a median? Okay. Let me put it this way. You have this x1 up to xn. I get it to the middle rank observations. So this is also a function. Because no matter what you have, I always map it to the middle rank. That means that is the quantity that half of your sample is bigger than it, half of the sample is less than it. So it's also a function. How about the minimum of x among all this? Is it a function? Everything is a function. So you got x1 up to xn. So I look at the minimum of it, then I just map it to that minimum. So it's a function. All right. Maybe it's hard to see in this one. So suppose I have n equal to 5. So these are the numbers. All right. So I ask, what's the minimum? Obviously, you know that this is the minimum. So when I see all this, it will automatically map to 1. If I have another sample of size 5, it's 2, 100, minus 2, 1, and 0. Then what's the minimum? The minimum is minus 2. Right? So that is what we mean by minimum. So whenever you have x1, x2, x3, x4, x5 as a random sample of size 5, I map to the minimum. So the minimum will be the one with the smallest value. So this function is called statistic. So you can come up with many statistics. All right? So because it's a function of the random variables x1 up to xn, so itself is a random variable. Right? If it's a function of all this x, I'm sorry, this is not. Let me exclude this one. Although it's a function, but this is not what we want. It does not make sense. All right? It's useless function. We exclude those. All right? So this function of random variables, really you can see some x inside. So it's again a random variable. So a statistic is considered as a random variable. So naturally, when we say about random variable, we want to know the distribution. How does this random variable behave? So we need to know how this random variable behaves, and the probability distribution of this statistic, which is a random variable, is called a sampling distribution of that random variable. So in particular, in this section, we talk about sample mean, which is the average of the random sample. So how does this X bar, we call it sample mean, how does it behave? All right, so this is the definition of sample mean. Average of all the sum of x1 up to xn. But once you observed these random samples, so now you take a random sample and then you find that, okay, you see x1 up to xn. Then this, we call it a realization. All right. So I hope you distinguish the two. One is a random variable. So it's a variable. Consists of a range of values and the corresponding probabilities. But then once you check and measure or do the experiment, you have the outcome. We call it the realization. Just remember when toss a coin. Before you toss a coin, there are two possible outcomes. That's why it's random. All right? They can be head or tail. But once you toss it, then, unless you close your eyes and you don't look at the outcome. Once you look at the outcome, there's no more a random variable. It becomes a realization of your experiment. So if it's a head, then this little x1 will be a head. All right? So you have to distinguish between the two. So this one is considered as the realization of x bar, the random variable x bar. So this is my sample, and these are the random represent the sample. But once I check, this sample, I have 1, I have 2, I have 5, all right? Then I just take the average of this. Suppose I have sample size 3. Then I just take the average of this one. So that is the realization of this random sample, which has value 1, 2, and 5 for size 3. All right. So these are the x, little x. These are this just a random variable. All right. So here is an example. We consider a discrete uniform population. So that means this population is represented by, okay, this is the population, 3, 5, 7, 9, 11. All right, so the population size is 5. And each one has equal probability of being selected. So to describe it, I can think of it as this population is represented by this probability function. It takes the value 3, 5, 7, 9, 11 with probability 1/5 for each of them. All right. So that's how we describe the population. Finite, infinite, we can have way to describe it through this probability function or probability density function. So this is the one. All right. Now, so the population mean, I work it out, is equal to 7. All right. Remember, mean is not the average. It's not sum of them and then divide by the number of observations. In this example, yes, but you should always use this formula. It's a weighted average. Each value is weighted by f of x, which is the probability of taking that value. So your sum of all this value divided by the number of observations, or number of the size. So in this case, sum up all the values divided by 5. Is true because they are discrete uniform distribution. All right. That is all the f of x here are the same in this example, which is 1/5. That's why I take it out. It looks as if I just sum up all the number divided by 5. But this is a special case. You must use this to get the mean, the population mean. So population mean is 7, and population variance is 8. All right. So now I take a sample of size 2. So these are the possible samples. All right. With replacement. remember we just mentioned earlier, with n equal to 5 and n equal to 2. With replacement, that means you can put it back and then select again. So altogether, there are 5 squared, or in this case, 25 possible samples. So you can have 3, 3, or 3, 5, all right, and so on. So the sample mean for this one is 3, for this one is 4, for this one is 7, for this one is 8. All right, so these are the sample means. Did I miss any possible sample? No, there are only 24. So what is the chance that you got this sample? What's the chance of getting this sample? All these samples are equally likely. So it's 1 over 5 squared, or 1 over 25 for each one. All right? Then the next question is, what is the distribution of x bar? Or before that, what is the probability of x bar equal to 7? X bar equal to 7. Then x bar equal to 7 means that you may have this sample, you may have this sample, you may have this sample, and this sample. So there are 5 out of 25 of this possible sample will give you a sum, give a sample mean equal to 7. So in other words, probability of x bar equal to 7 is 1 over 5. How about probability of x bar equal to 11? Then I check all this except this one will give you, and this is 1 over 25. So you consider all this and then you able to compute how x bar behaves. All right? So this is the distribution of x bar. All right? So this is how x bar behaves. Then I ask the question, what's the expectation of x bar? So I work it out. So it turned out to be 7. And what's the variance of x bar? All right, variance of x bar. It turned out to be 4. It's just a simple exercise. I have the distribution of x bar. I have all the values and the corresponding probability, so I can compute these two. Then I notice that this equal to 7 here, and this we show that it's also 7. This one is 4. And this one is 8 over 2. All right? 8 over 2. And what is 2? 2 happens to be the sample size. All right? So, now, at least for this particular example, expectation of x bar equal to expectation of x. That means what you expect about the original population, the expectation of x, the original mean of the population, okay, is the same as I expect from x bar. What it means is that, okay, you have this population, there's this expectation of x, which we don't know. I take a sample, got x bar. Take another sample, got x bar. Take a third sample, take infinite number of them, and then take the average. That is what we mean by expectation of x bar. So this should be the same as expectation of x. All right? And variance of x bar is equal to variance of x, not the same, but divided by n. Divided by n. N is the sample size. So, from here, immediately we know that this x bar, it behaves, all right, in such a way that it has the same expectation as the original population. Not only that, the variation of x bar, that means the value of x bar will fluctuate, but the variation is smaller than the original population. How do I know that? Let me repeat the statement. I'm saying that the variation of x bar is smaller than the variation of x. How do I know that? because variance of x bar is equal to variance of x divided by n. N is a number bigger than 1. So for example, 2 is half of the variation of x. If n is equal to 16, if n equal to 10, then the variance of x bar is 1/10 of the variance of x. All right? So think of it. If n equal to 100, then the variation of x bar is 1/100th of the variance of x. How about if n is 1 million, then the variance of x bar is 1/1,000,000th of the variance of x. So getting bigger and bigger the sample size, your variation of the x bar will be very close to the expectation of x. There's no variation, almost no variation. The variation is so small that it's almost no variation. All right? Okay. So here is a theorem about the behavior of the sample mean, which is 1 over n summation xi. All right? I from 1 to n. So we take a sample size n from an infinite population or a finite population with replacement. Just remember, from drawing random sample point of view, you have a finite population, but once you take it, you put it back. So that means the next sample value or the random sample that you select is the same distribution as the first one, because you replace it, so it's the same behavior. All right? And this population with mean mu and standard deviation sigma. Then the sampling distribution of sample mean has an expectation the same as x, expectation of x, and the variance of x bar is equal to the variance of x divided by n. All right? I have not said anything about how to describe the distribution. I only give you two information. One is what is the expectation of x bar, and the other one is the variance of x bar. I did not say, x bar follow an exponential distribution, or x bar follow a chi-square distribution, or x bar follow a normal distribution. I did not say that up to this point. I only say that expectation of x bar is the same as expectation of x, same as what the population's mean is, what we expect from the x bar. Remember, it's the expectation of x bar. It's not x bar itself. It's the expectation of x bar. What do you expect about the x bar? That means you have to get many samples, and then out of these so many samples, you calculate x bar for each sample, and then the average of all this x bar will be the same as the expectation of x. All right? So similar for the variance. All right? So this is what it means if you don't get the notation. So that's what it means. Okay. This is a very, I mentioned earlier. So this is something called a law of large numbers. And there's two versions. What we have here sometimes referred as the weak law of large numbers. But don't worry about it. All right, the strong law is more complicated. Okay, what it says is that the probability close to 0 for this event. What is this event? This event saying that your sample mean compared with the actual mean, mu. This mu is the expectation of this mu. The mu is the expectation of x. And sigma square is the variance of x. So it's saying that the difference between your random variable and the expectation of x, which is mu, right? This difference greater than certain value epsilon, all right? And the chance is approaching 0. as n goes to infinity. So what is saying is that, okay, if you get an n for a fixed n, then I calculate the probability, how likely that this one is bigger than epsilon. Epsilon can be any numbers. 1. I don't like 1, too big. 0.1, still too big. All right? So I try to look at how likely that your x bar is very close to mu, so that the chance of this difference greater than this number is very small. So that means it's unlikely that your x bar is too far away from mu, provided that your n is big. All right? So that's the idea. So if your n is big, 100 may be big, 1,000 may be big, 1 million may be big. So this is simply saying that if your n is big enough, it did not specify what is the magnitude of n. In fact, it depends on your distribution. All right? So it's just saying that x bar is close to mu. In what sense? In the sense that your sample mean is very likely that will not exceed will not get out of. Okay, so translated, it means that x bar minus mu within 0.00, a small number, all right, and this one. This is what it means. So in other words, we're saying that x bar, all right, is between this and between this. Between these two points, mu minus epsilon and mu plus epsilon. If epsilon is very small, so then we're looking at a very small interval. And the chance of x within this interval, this one is bigger. So this one, if this one is big, then that means the chance that it's outside this interval is very small. That's what this statement is saying. All right? Outside this interval, mu minus sigma and mu plus sigma is very small chance. So it's likely that it's very close to mu. So that's the law of large numbers. Large number means that you have a large sample size. Then your x bar, the sample mean, if you have a very huge sample, you get your x bar. Your x bar should be very close to the true answer. Although I still don't know the true answer, but it should be very close to the true answer, mu. All right. Okay, so as the sample size increases, the probability that the sample means differ from the population means go to 0. We're talking about probability. So there's still chance that the x bar will be outside this interval. All right, outside this mu plus epsilon and mu minus epsilon. So another way to look at it is increasing likely that x bar is close to mu as n gets larger and larger. So that's what we interpret about the law of large number. So here is an example. This one, a random sample taken from a uniform distribution with mean 0, 1. All right. So from here, we know that expectation of x, if you recall, then the expectation, if x follow uniform x AB, then expectation of x is equal to a plus b over 2, and variance of x is equal to b minus a squared over 12, if I remember correctly. All right, so that's how you got it. So now, I take a sample of x1 up to xn, a size n. So I compute the sample mean. Okay, I choose n equal to 3 million and epsilon 0.001. All right, so let x bar be the sample mean of this sample, x1, x2 up to x3 million. All right, then what is the variance, what is the expectation of x bar? According to the theorem that we just discussed, is equal to expectation of x, which is equal to half. All right, equal to half. variance of x bar is equal to variance of x divided by 3 to power 10 to power 6. All right? So it's variance of x divided by n. So which is a very small number. All right? So, so what I'm trying to do is to show that this probability, this is mu, and this is my epsilon, and my n is 3 to power 10 to power 6. So I want to compute this probability. How to compute this probability? Do we know the distribution of x bar? We don't know. All right? Of course, later on we have this central limit theorem, but we don't know. What we know is the expectation of x bar. What we know is the variance of x bar. So can we, based on these two, to calculate, maybe not exactly the answer, but give some information about this probability? So that leads to our Chebyshev inequality. All right? So in this case, I try to write it as k times the standard deviation. You remember probability of any random variable minus the mean within k sigma 1 over k squared. Check, huh? So this is the Chebyshev, one form of the Chebyshev inequality. So I just express this as k sigma. All right, so it turned out that k equal to 6. K equal to 6. All right, so apply the Chebyshev inequality, so it's less or equal to 1 over k squared. So at least I know that the chance of the sample mean outside the mean plus, so outside this mu plus 0.001 and mu minus 0.001. So the probability of x bar within this one is 1 minus 0.02778. So in other words, outside this range is about only about 3%. All right. So we're quite confident that our x bar should be very close to the mean, the true answer mu. All right. So it's about 3% chance that it will be outside this interval. Outside this interval. All right. Okay, I think I have to stop here and continue this Thursday on the central limit theorem and the rest of this chapter. All right. And start from chapter 6 on estimation, chapter 7 on hypothesis testing. And I think, yeah, only 7 chapters. This is week 10, right? Half already gone, right? At least for this module, for this lecture. So we have another lecture for this week. Then 11, week 12, and week 13.